In this video, we present mathematical sketching, a novel, pen-based, modeless gestural interaction paradigm for mathematics problem solving. Math sketching derives from the familiar pencil and paper process of drawing supporting diagrams to facilitate the formulation of math expressions. However, with a math sketch, users can also leverage their physical intuition by watching their hand-drawn diagrams animate in response to continuous or discrete parameter changes in their written formulas. Using a tablet PC, a user can create math sketches with a stylus. The user first draws a spiral object. If the user makes a mistake, a scratch-out gesture is used to erase the drawing. To vary the angle of the drawing about its center, the user begins by defining a function labeled a, and uses a lasso gesture to recognize it. Note that the recognized expressions are redrawn in the user's own handwriting. The user enters the animation time, and the O in the word to is recognized as an N. The error is corrected by erasing and rewriting. Drawing a line through the math and tapping on the drawing makes the angular association. Clicking on the Run button animates the sketch. To make the spiral object also translate along the x-axis, the user writes a function labeled x. In this case, we demonstrate an implicit association where the user simply labels the drawing. The user also makes a stretchable object by nailing it to both the paper and the spiral drawing. The user can graph equations by using the graph gesture. Graphing parameters are changed by writing them in and hitting the Update button. Solving an equation is done with a squiggle gesture. In this example, a user explores velocity versus acceleration with a speeding car and a police car. After graphing the equations, the user sees that at 10 time units, the cars will have traveled the same distance. The user makes implicit associations to label the speeding car with an M and the police car with a P, then labels the road length and runs the simulation. In this example, the user draws a simple pendulum. The equations on the left specify an initial angle of the pendulum that does not match the drawing's initial angle. When the user makes the association and runs the simulation, it is easy to identify there is a problem. This problem can be resolved by labeling the angle with the initial condition, which rectifies the drawing. In our last example, a user is interested in exploring an undamped harmonic oscillator. After writing in the equations, the user makes a spring and draws a block underneath it. After associating the mathematical specification to the drawing, the user runs the simulation and observes the effects of the sketch. The user then wants to see how increasing the mass affects the simulation. The simulation shows that increasing the mass actually speeds up the oscillation, which contradicts the user's physical intuition. After examining the equation for angular frequency, the user sees that the equation should be a equals the square root of k over m, instead of the square root of m over k. The user changes the expression and reruns the simulation. The block should oscillate more slowly as the mass increases. The user quickly checks this by increasing the mass from 10 to 100. The results now correspond to the user's physical intuition and show the math sketch is correct.